For joining us today. This is the, I don't know which number of ML meetups at Yandex Hall. So today I'm going to talk about scaling laws. Let me see if I can start the slides now. Yeah. So I'm Hrant Khachatrian. I'm leading YerevaNN and ML research group at Yerevan State University. And we're working on different topics in AI, and recently we have seen that apparently all those directions that we are working on are converging across one dimension, which is the scaling laws. And this topic is becoming the most important idea that our projects are kind of touching. And I wanted to present what's going on here as well. So, what is a scaling law? When we say scaling law is a formula that allows us to predict how larger compute will translate into better performance. So if you add more GPUs or add more time of processing, will it help your model to become better? So the law, the formula that guides this progress, depending on the compute you throw at your problem, is called the scaling law. This is probably the most important concept of the recent AI developments. Like everything that we have seen in ChatGPT and the likes are coming from this concept. Researchers at Google and OpenAI discovered that you can improve the performance of your model by adding more compute. And they found neural architectures and experimental designs that allowed this growth of performance depending on the compute. So when I say larger compute, it means actually two things. First, it's more parameters, so your neural network can have more and more and more parameters. And the other dimension is data. Okay, so we can increase number of parameters and we can increase the size of the data set. So throughout this entire presentation, we will use this notation. So N will always mean number of model parameters. D will always mean the number of tokens. When I say number of tokens, it already implies that we're going to talk about transformers, right? And first of all, text. And the compute is the product of these two quantities. The unit of compute is floating point operations, flops. So when you want to compute actually the number of floating point operations that your GPU performs to run a neural network with n parameters on d tokens, this number of operations is usually around 6 times n times d. It's not very hard to compute. I mean, it will take time on paper to write down what are the operations in transformer, how many matrix multiplications, and so on. And this has been done in multiple papers, so just believe these numbers. So if you have n and d, the compute in flops is 6 and d. So the main question here is why we need these scaling laws. The first obvious reason is the predictive power of scaling laws. So if we know in advance how well our model will perform if we add more GPUs or add more parameters or add more data, that's very important, right? Because you have heard from rumors that, I don't know, training GPT-4 costed, I don't know, $10 million or I don't know, $100 million, right? You don't want to spend $100 million of compute on something that will not work eventually, right? So it's better to predict first what will be the performance of this huge model. The second reason that why people look into the scaling laws is that when you work on those large AI models, you care about ideas that scale well. Okay, so this is very important, and this is very unusual for most of us. Like, I think 99% of AI researchers and practitioners do not think this way. Usually it's the opposite, right? We are looking for ideas that will make our model smaller, that small model can do something better, find a trick that works on 100 million parameters or 10 million parameters. But when you're trying to push the boundaries of AI, when you want your AI to do new things that were previously not possible, you want ideas that will work on larger scale, not on the smaller scale. So that's the filter of your kind of thought, right? And this is where scaling laws help, because you can check your ideas and try to see how these ideas affect the formula of scaling, right? And then there is another reason people are very much interested in scaling laws. This is the optimal compute problem. So if you know that you have, I don't know, 1,000 GPUs and you have 1 month of time, you want to know how many parameters you should use and how much data you should use. Because you can use these GPU hours both on number of parameters and on the number of tokens, right? There is a trade-off. And in order to find the right point, you need to know how does your model scale across number of parameters and across the number of tokens. So the first attempt of finding a scaling law was done in this paper. Everyone calls this Kaplan scaling law because of the first author is Kaplan. And you can note that the last author of this paper, who essentially led this entire project, is Dario Amodei, who is now the CEO of Anthropic. He is blogging very often recently. So this was the first team that published how you can actually scale. So, so the notation I'm trying to keep in the slide always. So n is the number of parameters, d is the number of tokens, l is the loss, okay? And you can see that we have like 4 variables here. Some of them depend on each other. And reading these plots is always complicated because we have more than 2 variables and we want to plot everything on one plot, right? So on the left side, you can see that x-axis is tokens processed, which is D. And y-axis is the loss. So we also want to show n, right? The number of parameters. So we encode n by color. Okay? So yellow is the largest number of parameters. Blue is the smallest number of parameters. And you can see that they covered a very wide range. They started from, I don't know, 1,000 parameters. I don't know what is a 1,000 parameter transformer, but they had it. And up to 1 billion parameter. And this shows the loss as they trained it. It shows that the left image shows that larger models require fewer samples to reach the same loss. This was also a little bit counterintuitive to me when I first learned about this. Hrant Khachatrian told me about this one day during one of the calls, and I was like, what? Like the larger model should require more data to figure out what's going on, right? But it's not the case. So if you're training language models, huge models, even if you start from scratch, they need less data to figure out what's going on. And by the way, this is the reason that when people ask me, why don't you train Armenian language models, we have more Armenian data, I say it's not useful because those companies who have large models, they need much less Armenian data to get to the same accuracy than I need, right? So the right picture is basically the same, but the x-axis is different. Now the x-axis is compute. So it already includes the n, okay? That's why the yellow chart is like pushed to the right because it has most parameters. Yellow lines went to the right. And here you can see that for the fixed compute, like they have 10 minus 3 there, right? For 10 minus 3, if you go up and find the lowest point, that's the compute optimum. Because if you continue to train the large model, at some point it starts to behave slower. It starts to become better slower than a smaller model. Right? You can see that at some point you want to get to a larger model and train less on less data than to continue training the small model. So compute optimal is this bottom frontier of this chart. So if you know how much time you have, how many GPUs you have, you just take the point and then take the smallest value and see which color is that and take the model of that size. Okay, so this shows how you can do trade-off between model parameters and data. Unfortunately, okay, this is also important before I go to unfortunately part. So in this paper, LSTMs were still alive, and they wanted to compare the scaling laws for LSTMs and transformers. So they showed that for LSTMs, if you increase the number of parameters, it doesn't scale as well as transformer. So blue here is transformer, and you can see that for every model size, if you increase the number of tokens on the right chart, blue is below red. I think this chart was the death of LSTM for those large companies, right? Because this shows that transformer is scaling better. Even if you don't know the coefficients and so on, this visualizes that if you want to scale to, I don't know, 10 billion parameters, it's better to do with transformers. I think since then, no one even tried to scale LSTMs anymore, right? And yeah, they found, when you do these experiments, when you do a lot of trainings with different N's and with different D's, then you can find a formula that will fit this value, right? So for every N and D, you have the corresponding loss, and then you want to find a formula that would fit. So they took this formula for some reason and could fit it and got some results. So once you have these coefficients, then you can analytically figure out the compute optimal, for example. Right, but then, oh yeah, and these are the coefficients, by the way. So here you can see that NC and DC are constants. N is what we know, number of parameters. D is the number of tokens. So if you increase N and if you increase D, these fractions become smaller and smaller, which means loss becomes smaller. And these coefficients guide how fast they become smaller. Right? So the most important things here are alpha N and alpha D. It shows that on average in their scenario, data is more important. So for with more data, you could scale faster than with more parameters. And this is what was their first and important mistake. So in the next paper that I'm going to show you, the authors wrote this, that there is a significant problem in Kaplan paper. The problem is that they used the same learning rate schedule for all their runs. So this visualizes. So on the left part, in all the charts, the x-axis is the number of tokens, essentially. Okay? So and on the left side, you see the learning rate. Okay, so the blue one is the normal learning rate schedule. When you know you are going to go up to 8 million sequences, you want your learning rate to decay fully to the to that level. right? But then if you want to train longer, you change your learning rate schedule towards upper ones, towards brown, pink, which the learning rate schedule will end much later. So here they show that if you are going to stop at 8 million sequences, the blue one is the best. So if you want it, if you train for very long, on a very large data set for very long, and you kept the checkpoint at 8 million sequence, like for example, if you took the pink one and trained up to the end, but then took the checkpoint at 8 million sequences, that checkpoint is not good. If you trained with a proper learning rate schedule that would finish at 8 million sequences, that would be better than if you early stopped the longer training. Okay? So this means that they underestimated the power of small models. Okay? So that's how they write here. We find that setting the learning rate schedule to approximately match the number of training tokens results in the best final loss, regardless of model size. For fixed learning rate schedule, the intermediate loss estimates are therefore overestimating the loss of a model. So actually, the real loss would be better if you had a proper learning rate schedule. So after this quote was from this paper, which is, the title says Training Compute Optimal LLMs. The authors are Hoffman and others, but everyone knows this paper by Chinchilla, because Chinchilla is the name of the model that was used in this paper. So you search for Chinchilla, it doesn't bring up this paper, because nowhere you can see Chinchilla. So in Chinchilla paper, they proposed a kind of easier formula. They say, again, n is the number of parameters, d is the number of tokens. The loss function is actually E. E is some lowest possible loss. It's kind of an entropy for your data, right? You can get better than that. And then you have two independent numbers which depend on the number of parameters and number of tokens. So they trained a lot of models. If you look at the left image, again, x-axis is the flops, which means that it is already the product of the number of parameters and number of tokens. And y-axis is only model size, which is n. Okay? So for every n and every value of d, they trained one model, and these dots on the left are these models. And they learned the loss. The loss is encoded by color here. And they fit the formula that I showed on the previous slide. And then drew the lines of equal loss. So here, yellow towards white is higher loss, which is not what we want. We want lower loss, which is the darker colors. So it shows that on the top right, obviously, the loss gets better, right? That's expected. So what they did, they showed that for if you have some budget, for example, you can see that there is written Gopher budget. Gopher was a GPT-3 level model by DeepMind, and it was trained exactly the same way as GPT-3. So now they say that with Gopher budget, the optimal point on these lines is 40 billion parameters. GPT-3 was 175 billion parameters. So this chart shows that if you use the same amount of compute that they used for Gopher or GPT-3, if you use that with 40 billion parameters, which means less parameters and more data, you would get better performance. So OpenAI trained GPT-3 in a non-optimal way because they relied on Kaplan scaling laws, which were incorrect. And Google repeated it with Gopher. And then in this paper, they showed that it's not the case. You shouldn't do that. So when they fit this formula on those numbers, they get these coefficients. It turns out that here you can see that n is a little bit faster than d, but not very different actually, 0.28, 0.34. They're power law coefficients. So the implication of this is that if you know one optimal configuration, if you want to find the next optimal configuration, it's better to scale n and d almost equally. Okay? And this is another picture that demonstrates essentially the same thing. So x-axis here is flops, compute, y-axis is parameters, and the green line there is what is predicted by this formula. That's the compute optimal line. And the stars above, the red star, orange star, and pink star, they are Gopher, GPT-3, and NVIDIA's Megatron. So all of them have used non-compute optimal ratio between number of parameters and number of tokens. So Chinchilla is the green one, which is, they predicted it to be on the green line. It was actually a little bit higher right here. And its performance was better than those 3 other stars. And one slide about how they kind of, I want to say, derive this formula, but it's not really derivation. It's more like, I don't know, convincing others that this formula makes sense. So they say that you can decompose your loss, which is L, into 3 terms. So you can, your loss is this LF bar ND. So you can add and subtract LFN and add and subtract LF star. LF star is this ideal model, like a bias estimator, whatever. The ideal model that could ever fit this data. LFN is the ideal model with infinite data. So if your distribution, if you can sample infinitely from your distribution, that's the ideal model that you can have with n parameters. So you can add and subtract, and the first term becomes E, your entropy. The second term does not depend on the data because it's in the limit of data to infinity. So that's the difference between the ideal model and ideal model with n parameters. And they estimate that by some fraction, where by some small power law, depending on the number of parameters. There is some theory that motivates that, but it does not predict any of those coefficients, or does not even predict coefficient. And then the last part is the ideal n-parameter model, and n-parameter model trained on limited data. That gap does not depend on n anymore, they claim. It depends only on d. So this law is now widely used, and then people trust this. A lot of other experiments have been done. It was shown that this law works on other types of data in other scenarios. And now I want to focus on what is missing in Chinchilla paper, what else we could expect from scaling laws, or what other things we are looking for. So the first problem is that this was designed for transformers and was trained, that were trained in an autoregressive manner. The second thing is that all these large trainings that we have seen, they use single epoch of data. Okay, so they have entire internet, like common crawl and a few other things. So they never run over the same data again. So everything here is trained for a single epoch, which is also quite unusual for regular machine learning, but that's how they operate in language models. This is done for text. This is done for single modality. And another important problem here is that this is predicting loss, but usually we care about accuracy, right? We have benchmarks where we have accuracies, we have other complicated metrics. We are eventually interested in those metrics, not loss functions. And this law also does not cover anything about test time compute. So there is one paper from Google, Google Brain Zurich, if I'm not mistaken, which is talking about scaling vision transformers. So this is still a transformer, but this is already computer vision. They have patches and so on. And they also did similar lines. You can see they took different sizes of models. So sizes here are not encoded in number of parameters, unfortunately. This VIT literature has their own notation, right? VIT-B, VIT-S, VIT-L, and VIT-G. So in this paper, there is a special table that has all these mappings, and we printed this table and put on the wall of our meeting room because every day you need these numbers. And they came up with some formula. So their formula is something like this, where C is the compute, okay? So they don't get into the details of N and D. D is also weird here because you have number of images, but these VITs usually are trained on multiple epochs, so you have to be careful what you think of D. But I think this is the only attempt to have a formula for computer vision related networks. Then this question for those who don't have enough data or and want to understand what's going on with multiple epochs, this became an important question, and a team from Hugging Face and a few other places did this. I think this was one of the best papers in NeurIPS 23, scaling data-constrained language models. I think this picture summarizes the paper very well. If you look at the dotted line, the orange dotted line on the left, that's the scaling law as Chinchilla would predict. Okay, so if your entire data set consists of entirely new tokens, then that's the law. Again, on a y-axis you have test loss, and on x-axis you have tokens. So this is for a fixed size of a neural network. But if you repeat your data, the actual curve gets slower, right? So it does not go as fast as your dotted line. And they claim that up to almost 4 epochs, you don't see much difference. Okay, so for the first 4 epochs, every new epoch acts as the same data, more or less. But then after 4th epoch, the gap starts to become more and more visible. So after, I don't know, 40 epochs, repeating does not help anymore. You might even get into overfitting, but this paper does not cover overfitting properly. Which means that the optimal line is actually getting lower than Chinchilla. So on the right side, you can see a plot of tokens versus parameters. And there it's obvious that if you repeat your data, the relationship between N and D gets worse, right? So more tokens do not bring enough value. It's better to scale on the number of parameters. So they take the Chinchilla formula and try to change a few things there. So they say instead of D, now we have D prime. And D prime is UD. UD is the data size of a single epoch. And then for each next epoch, the contribution of the tokens is getting scaled by this weird parameter. And this parameter gets smaller and smaller as you accumulate epochs. Okay, so this just says that this more or less fits the data that they had. And in our practice, this also is more or less verified. So we didn't really check the numbers, but recently we had a training with small molecular data set where we had to go with multiple epochs, and we went up to 6 epochs, and the curve looks pretty okay. What about other modalities? So Armen Aghajanyan's team did a very large project in terms of compute in Facebook about scaling laws for other modalities. And Karen from our team had a small contribution there as well. So the formula is the same. You can see that it's still L and D equals E plus some what they call functional approximation error, and the other one they call convergence error. So the coefficients are different for different modalities. Okay, so for text, they found these coefficients. It's actually different from what Chinchilla found, but it comes from the data source. Okay, so the data set was different. But it's interesting to see that, for example, for code, alpha and beta are larger, which means that code is getting better faster with more data and more parameters. And with images, it's the opposite. The alpha and beta are smaller, so it's harder to scale image-based language models. So this is a single, what they call unimodal scaling law, which means that in the training, they use images, but only images. Okay, like most of the modern, like GPT-4o, for example, is not unimodal. They use a mixture of images and text. So about mixture, this is the formula that I remember the meetings that Armen was brainstorming. When you have a mixture of two modalities, then the loss, what Armen managed to fit, looked like this. So you have the average of the two loss functions, like two scaling laws, essentially. That's the first part. Then there is some maximum level of synergy you can get from these two modalities, because it's possible that there is some synergy, right? Between, for example, text and code, it's obvious that there should be some synergy, right? But for other modalities as well, there is some synergy. And then there are kind of competition. And what Armen observed is that this competition is more obvious when you are in the smaller scale. So when your model is small, your two modalities compete with each other. But when the model becomes large enough, this competition gets less important. You see the competition term also has n over alpha, n to the power of alpha. So if n goes higher, competition gets smaller, and then the effect of synergy becomes visible. So what they did, they actually did an experiment with speech and text. So they took a bimodal, which means half of the dataset is speech, half of the dataset is text. And they did this, you can see on the left, x-axis is number of parameters, y-axis is number of tokens, and the color is the fitted scaling law. So these crosses represent the small models that they trained. So they trained up to 10 billion parameters and up to 10 to the 11th power tokens. They fit the scaling law, and they saw that there is this dashed black line. So if you go beyond that line, then the synergy term will be larger than the other terms. So you will get synergy effect of training on the combination of text and speech. They will start to help each other. And they actually did the experiment, and it was correct. So they took a 30 billion parameter model, and trained for 40,000 updates, and they got below this dashed line on the right, which is the essentially it shows the first term of the law, which is the average of the two losses. So this showed that if you mix modalities, then you could get improvements in both modalities if you go beyond some compute level. This was ICML 2023. Now, a couple of things about downstream tasks. Okay, so we know that we can more or less reliably predict loss, but what about downstream task? This paper was from a lot of people from different places. I think it was led by Ludwig Schmidt, who is in University of Washington. Here, what they did, they first tried to go towards overtraining. What does it mean, overtraining? Overtraining is when you train for many more tokens than compute optimal. This is important because even if it's not compute optimal, you eventually want to have a small model for inference, right? For example, GPT-4o is well overtrained. It's a small model relatively, or 4o mini is even smaller, but they are trained on a lot of tokens, well beyond compute optimal, to get better performance and to keep the model small. So this paper actually verified that the Chinchilla scaling laws still hold for the scenario when D is much larger than the compute optimal number. That's what is visible on the left side. So these pink dots are overtraining, and these light blue dots are compute optimal in terms of Chinchilla. So when it says M equals to 20, that's the optimal ratio of data and parameters according to Chinchilla. M equals to 300 or 600, that's very serious overtraining. So they showed that, so this, when the dot is empty, when this marker is empty, that's a prediction, and the markers that are not empty are the actual numbers. So they showed that these empties and non-empties are very close to each other, which means there is predictive power for overtraining regime. And then what they did, they took 17 tasks and computed the performance on each of them and took the average. Okay, 17 downstream tasks and their average error. And they managed to fit this error with this formula. Here, L is the loss. So if you know the loss, and we know that we can fit the loss with scaling laws and so on, now you can have a scaling law for error. Average error over 17 tasks. Okay, this is very important. So they didn't manage to make it work for any single task, but if you average out over the tasks, then apparently loss becomes a good predictor. And this is the formula. The formula is this gray line on the right, on the right plot. And you can see that even for overtrained models, the prediction and the actual value are quite close. So at the end of their paper, they have a very long list of limitations of their paper. And I want to focus on a few things here. The first is post-training. They say that none of these things actually involve fine-tuning. Right? Usually when you have a large pre-trained model, you can fine-tune it before you apply on a downstream task. So here the downstream tasks are text-based tasks, which are directly asked to the pre-trained language model. No fine-tuning wasn't done here. So when you do fine-tuning, you make things much harder to predict. The other one is individual downstream task prediction. That's what I said. So they were not able to predict downstream tasks individually. They predicted the average of many tasks. And they don't talk about dataset curation, which is another important question, right? They took one existing dataset and did that, but a lot of things depend on the internal distribution of this, like inner distribution of these datasets. And recently there was another paper that attempted to predict performance of a single task. They also did it with 2 stages. The first stage is the same Chinchilla scaling law, which is you predict the loss, not the loss of the entire model, but the loss of for this particular task. So if the task is a, I don't know, pair of questions and answers, right? It's text you can write down and compute the loss on this, or perplexity on this particular text. So on the left side, you can see what they did. So with less tokens and smaller number of parameters, they could fit a Chinchilla-style scaling law and apply it on a larger model, which was 7 billion parameters and 13 billion parameters, trained on much more tokens, up to 5 trillion tokens. And the prediction was pretty good in terms of loss. It was 0.2% error or whatever. And then with the second stage, they did something similar to this one. They used, I think, I don't have the formula here. They used sigmoid function that maps from task loss to the task accuracy. Okay, so they figured out that the general perplexity of the model is not that useful. You should look at the loss on the text that belongs to this task. And then you can fit a sigmoid-like function that would predict the accuracy. And if you do these things together, like if you combine these 2 laws, you get mapping from number of tokens or number of parameters directly to task accuracy. And it was more or less okay, right? 1% error. But what was funny is that it didn't work for every task. So here they show the breakdown over 8 tasks. And for some of the models, the error is like 1%. But there are 2 problems, this ARC, for example, where the error is more than 10%. So it completely failed to predict what's going on there. So this shows that it's still very hard to predict the accuracy of specific downstream tasks. By the way, they did other kinds of averaging during this process. So if the previous paper took the average over tasks, this paper took the average over, they say, the last 5 checkpoints of each model. So it's not that they take 1 checkpoint as their source of data. They take 5 last checkpoints, they compute, and they take the average. So there is so much noise in this process that they're trying to kind of smooth it with all these types of averaging techniques. Finally, test time compute. So I took these bad screenshots from somewhere. I still didn't find a proper scaling law for test time compute. But I think this particular chart that OpenAI showed in late December about O3 is kind of shows that they have their internal scaling laws, right? If you look at the O3, there is blue part and there is light blue part at the top. And during the demonstration, they said that it's when you ask O3 to think more, right? This is like very long compute or long thinking. They said that it might, I don't know, cost a few $1,000s to answer a single question, right? So this difference between the dark blue and the light one shows that there is some scaling law there. If you scale the thinking process, if you let the model think more, it gets better number. And I'm sure that someone inside OpenAI took these numbers and fit with the formula, right? But it's not publicly available, so we don't know the forms of these scaling laws. So one last section of this presentation. It's about our work. So we have an algorithm that Philip presented in this room a few months ago. It is a genetic algorithm to optimize molecules, to find good molecules, and it uses LLMs in the loop. Okay, so imagine we have a pool of molecules. What we do, we sample a few molecules from the pool, give it to the language model as a prompt, and ask language model to generate new molecules. And then we score these new molecules and keep the best ones in the pool. We update the pool with better molecules from the newly generated ones. It's exactly genetic algorithm, right, in a way, or evolutionary algorithm, where you call language model in a loop. So the final performance, the final quality of the molecules that you have found depends now on the size of the language model, on the data used to train the language model, but also the number of iterations of this genetic algorithm, right? Because if you can iterate more and more and more, you might find better molecules. So now we have one more dimension, which makes it much harder to model and visualize and everything. So what Tigran did here, he temporarily removed the data dimension. So you can see that there is no D in this formula. There is only N. And he empirically found that this formula fits the data more or less well. So he took 4 size of neural networks, 170 million parameters up to 1 billion parameters. They are llamas initialized from scratch, okay? So no pre-training. Very small version of llama up to 1 billion version of llama. And he trained them on some data, fixed amount of data, and ran this genetic algorithm for k iterations. He took up to k equals to 20 and used and fit a scaling law. So here you can see a chart where x-axis is the number of parameters of the neural network and y-axis is the number of iterations of a genetic algorithm. And the entire training was done in this shaded area below. Okay, so initially we did up to 20 iterations and up to 1 billion parameters. By using these points of data, we know the actual performance, right? We fit this formula and try to see its predictive power. So this formula predicts that if you go to 3 billion parameters, which is the next size of llama, and you go to 50 iterations in genetic algorithm, you should get 0.92. And Tigran actually did that and got to 0.919, which is pretty close. And then, when looking at these numbers, we decided to test what would be to run the genetic algorithm much longer with a smaller model. Because this particular formula implies that there is a trade-off between N and K. You can have smaller model with more genetic algorithm iterations versus large model with less iterations. Okay, so it turned out that if you push this formula to its limits, if you go to 100 million parameters, I think 170 million parameters, and push for 160 iterations of genetic algorithm, it doesn't fit very well. So it actually gave 0.911, which should have been closer to this orange line, not the yellow line. You see 0.911 is clearly less than this yellow, which is constant 0.92. So actually, the smallest model that we tried didn't scale according to the law that we predicted. But the next size, which is 300 million parameters, it is going very well. It actually went exactly 0.92 with more than 100 iterations. So it shows that the scaling law works almost for every size, but not for the smallest size we tried, which might mean that, I mean, all these scaling laws probably have some limitations, right? But this could also be because of the not so clever choice of this formula. Maybe it's possible to find a formula that puts a limit on how much small models can go. Probably there is some saturation there. So the smaller models, after some number of iterations, saturate and do not go beyond. So this is what we will explore in the next weeks. And we hope to come up with a formula that takes into account both N and D and the number of iterations of genetic algorithm and gives us proper predictive information about our larger trainings. By the way, this was tested on an average of 5 optimization tasks. Again, this is not a single task. That's also, or 3, I think. No, not 5, 3. This is an average of 3 tasks. That's it. Thank you. And this is a feedback form. This is a general feedback for this series of events that we do with Yandex Hall. And we will be happy to see what you think about it. And I'm open for questions. There should be another microphone here. Here? No? Not here. Where is the other microphone? Oh, it's here. Okay. Yeah, questions. Okay. Let me use the opportunity to drink.
So, could you explain this results? It's you just try to train your models, try to measure your loss and your accuracy, and after that you try to get scaling law formulas. Yes, this is approach from the. It's not theoretical. It's just try to formulate saved data.
Yeah.
Measured data.
Yeah, we actually measure it, and the idea is to do that with smaller models so that you know what will happen if you scale. Okay, so the whole idea of this chart, for example, is that computing and doing these experiments in this shaded area requires less compute, all these experiments together, than one experiment on the right, because the models get very slow, right? And if this predictive power goes beyond this number of parameters, I mean, if we had more GPUs, we would definitely try to go to 7B and 7TB, right? Now it's the bottleneck is the compute for now. But yeah, that's the idea.
I have a question about the low amount of data. So maybe this is just the difference between the average of 3. So if you repeat this, maybe it will, not 3 times, but 100 times. Maybe it will be closer to the correct result.
You mean the top one?
Yeah.
It's actually repeated 10 times or something.
10 times,
yeah.
and still not fit.
Yeah, so it's an obvious problem with the law. More questions?
Thank you for presentation. I have one question. How do you get that equation trying some model training, and how you find that equation?
That's a good question. You are trying to do something reasonable that you think would correspond to something, and then you sometimes look at your data, but you have to be careful to not look at the data that you are going to extrapolate to, right? So when designing this formula, our teammate Tigran looked only at this points in the training area and tried a few things, and this one worked the best. But in general, you have some intuitions, right? You know that with larger models it gets better, for example, so it means that n should be, I don't know, in the bottom part of the fraction, right? And then k, how it affects and what are the coefficients there. So you usually find the raw structure of the law and then add more coefficients to fit. If you see that, I don't know, without beta it doesn't fit, you add beta and see that now it works better, then probably it's there. But there is no theoretical justification to have beta here, for example. Okay, it comes from trial and error. In that sense, it's not really scientific, right? You're just empirically fitting something and hope that it works. But the magic is that it works in certain cases and it's very powerful.
Yeah, thank you very much, Ranjam, for the presentation. So maybe a naive question, I don't understand like whole presentation completely, but these scaling laws, what they predict, that the model will become, not your results, like just in general, models became bigger and bigger with more tokens, more parameters, and more like compute. Is there any like physical limit or something like that, or we just using this approach, we will make our models bigger and bigger and they will become better?
So the physical limit is this E. Okay, so depending on the data, if you fit this formula, it will tell you that you cannot go better than E. But it's usually okay, right? I mean, loss cannot be zero if you are predicting text, right? Because there is an internal ambiguity. Like if I'm starting a sentence, it's not possible to be 100% sure what I'm going to say next, right? So there is some obvious natural kind of entropy that you cannot predict. And if you fit the law, it shows what is the minimum possible loss that you can get with this approach. Is it the physical minimum? No one knows. Maybe the physical minimum is lower, but our models are not able to reach that. That's also possible, because computing E like with a theoretical analysis is very hard. It's hard to know what is the entropy of internet, right?
Yeah. For the last part, you mentioned that maybe for small models, they are like a saturation, right? And then they behave differently, like after some moment. Is it possible, like on larger and larger scales, there are also some changing in the scaling laws?
It's possible, but I think no one reported that so far. So there are these rumors that, I don't know, Ilya Sutskever said that we hit a wall or whatever, but there is no reported evidence that, you know, we tried on a 10 times larger data set and it didn't help. I don't know any such result. We have it for LSTM, right? By the way. So, for example, on the right part, you can see that the red lines become flat, which means for fixed number of parameters, you add data and it doesn't improve anymore, right? So for transformers, looks like we didn't find the end yet.
I was wondering about the quality of the data. There was a bunch of work, Microsoft Phi models and so on, where they say that very high quality data can be very helpful compared to common crawl and so on. So how is the data quality? I guess it's not reflected here.
It is reflected in the coefficients. So if you go to a better data set, this alpha will become better and you will scale faster, or beta, I should say.
And E is also kind of dependent on the data set. Right?
Yes, yeah. Everything depends on the data set, unfortunately. So all those things kind of are buried inside these numbers. And the idea is, one thing that we're trying to do with Aniala in our lab is to derive these laws. So the formula does not change, okay? It's only the coefficients. No one said that if you change the contents of the data, formula becomes obsolete. No, formula is the same. But how do you choose your data to have the best coefficients? So the hope here is that you can know that with small experiments. Because if you can fit these laws with, I don't know, up to 1 billion parameters and up to 10 billion tokens, maybe you change the data composition in this small scale and see which curve is better, and then do your largest experiment with that combination of data. That's the hope of this research, and that's what we're trying to do. I mean, it's obvious that people at Meta and OpenAI and Google have done that, but they don't report it. So today I asked Armen actually about it. He said maybe the Olmo papers from OpenAI can have this type of information if they did this, I don't know, experiment with data mixtures. So because they report.
Thanks a lot. Do you think it would work if you trained a model which you gave samples from your different data sets and then told what the actual coefficient is, and then try to fit that to an unseen data set? Sorry, predict for an unseen.
Probably yes, but you need a lot of data to train that model, right? Yeah, I think so.
I was just wondering, how do these scaling laws take into account the problem of vanishing gradients?
There is no problem of vanishing gradients in transformers.
Not at all, not
No,
in the slightest. If we just increase the complexity of the models.
No, actually, if you look inside the transformer architecture, I think this problem is more or less solved now, right? They have a lot of residual connections, and people know how to properly initialize them. By the way, there are some caveats, problems with initialization. For example, recently we learned that if you tie embeddings at input and output, then the initialization standard deviation should be very different. But it turned out that people knew about it, so it was new for us, but people have discovered that. So, but if you do these things correctly, I didn't talk about how do you choose learning rate, how do you choose batch size, right? And initialization, learning rate, batch size, and a few other things. If you do that properly, there is no problem of vanishing gradients, and it's not covered here.
Regarding the quality of data and downstream task, and maybe, you know, in some papers, did they try to learn this kind of scaling law, like for labeled data versus unlabeled data, pre-training step versus...
So most of this is about pre-training on unlabeled data. For these last ones that I showed you, this is, I don't know, labeled in a sense that it's question and answering. And yeah, there they introduced this concept of task laws, not regular laws, right? Because you're focused on the laws for your own data. I think other than this is very recent. I think this is December or November 24. Other than this, I don't know much work. So we are trying to do things like that, but when I think about this additional complexity of fine-tuning, which was mentioned in one of the papers, so when you do pre-training and then do fine-tuning, this fine-tuning adds its own source of noise. So it becomes harder to figure out what was going on in the pre-training. So now in one of the vision projects we don't do fine-tuning based evaluations. We are trying to do KNN based classification on the representations of pre-trained model so that we don't have any fine-tuning effect. But it's still early work, so we don't see the laws yet. It's very weird for now.
Thanks.
One more question here.
So one of your scaling law formula was for vision transformers, right? Was the scaling law created for autoregressive training or some BERT-like
No,
training?
this is BERT-like. Autoregressive vision transformers are very new, right? It came from this Apple thing.
Yeah.
This is
year.
earlier than that, no. I think this is even more complicated than BERT. I don't remember which one. It could be even supervised on ImageNet, by the way. I don't remember what they did, but this is the Google's attempt to get to VITG. This is the one that is on the wall of our meeting room.
So it's pretty old paper.
Yeah, it's like 2 years old at least.
Okay, thanks.
A question regarding the test time compute. So, especially for smaller models, isn't it like easy to get derailed when you scale the test time compute a lot? So like it generates like random stuff and then it gets like completely in a like weird place. Like I was doing some like translations for a couple of weeks, and especially for Armenian, where the like resources aren't that many, so the model doesn't know Armenian that well. For the O1 model, you can like scale from the API, you can scale the time compute, and then it like starts generating like in Hindi, in Russian, like whatever.
Yeah, but I don't know what is the reason for that, because you know these O1 style models are trained in a very weird way. It's not autoregressive at all, right? So I think that's part of the problem, because if you have seen in DeepSeek paper, in DeepSeek R1 paper, when they're talking about R10, they say that the model is mixing English and Chinese. And for the proper R1, they added an additional reward that was about keeping language consistent. This is probably the most complicated loss that you could put on. So I think those things, those RL-based losses derail this entire story. If you talk to people who believe in these scaling laws and play with them, they have this religious faith in simplicity of the models. They think that all of this is true because the cross entropy is a very simple idea, and autoregressive loss is just cross entropies over tokens, right? Once you get beyond that, I think RLHF like completely makes things impossible to measure. So I wouldn't be surprised if all these laws get broken after you do proper RLHF. But on the other hand, we hope to have something similar for vision transformers trained in a self-supervised manner, which is very complicated laws again. Teacher-student networks, whatever. And we'll see. I think in a couple of months we'll tell you if we figured it out. Okay, let's finish and we can continue networking there with water and stuff.